Okay, lads and ladies. I just started recording this class, which is your lecture for Friday. And I realized that I didn't have my screen share on through my little introduction there. So I'm going to back us up. This is your lecture for MAC2311, section 4, Friday, 10/23. This is the last of the pre-recorded lectures I'm putting together for you guys this week. Today, we're going to talk about the last few things from the syllabus that we have to cover before getting to applied optimization. So earlier in the week, we talked about linear approximation and min-max problems. On Monday, in addition to linear approximation, we also talked about section 4.3, which is the graphs of f and f primed. The book titles that section, How Derivatives Affect the Shape of the Graph. And we talked a little bit about curve sketching, but today we're going to fill the gaps. So the last things that we needed to talk about from this chunk is L'Hopital's rule and a more thorough discussion of curve sketching. So let me bring you over to the doc cam. This is what we are doing. We're going to talk about L'Hopital's rule and curve sketching. And L'Hopital's rule simply says this. I'll walk you through it carefully. You can write this down as we go. It says, if f of c is 0 and g of c is 0, and both of the functions f of x and g of x are differentiable at x equals c, then when you go to take this limit, if you just try plugging in, you're going to get 0 over 0. And what L'Hopital's rule says is, okay, 0 over 0, that's not helpful. That's an indeterminate form. Instead of going through that long process of trying to factor something out and cancel it, you can differentiate the top, differentiate the bottom, and try again. So if you're trying to take a limit of a ratio, a fraction, the top and the bottom are both going to 0, then you can differentiate the top and bottom and try again. In other words, this can be used when the limit as x goes to c of f of x over g of x looks like 0 over 0 or infinity over infinity. And L'Hopital's rule is basically, it's an alternative to the whole factor and cancel thing. L'Hopital's rule is an alternative to factoring and canceling like we did in chapter 2. So you remember back in chapter 2 when we were working with limits, specifically the limit that defined the derivative, all of those looked like 0 over 0 if you just plug in. All right, if you just plugged in h equals 0 in those difference quotients, the top and bottom were always 0. And there we had to do a whole bunch of algebra to factor out an h and cancel it with the denominator. Sometimes we needed to multiply by a conjugate, sometimes it was something else. But what this does is it provides an alternative to that process. Now, I couldn't have showed you this back in chapter 2 because we didn't know how to take derivatives yet. Chapter 3 taught us how to take derivatives using differentiation rules. So now we can kind of come full circle and return to limits of that style and take them using L'Hopital's rule. A quick note, this doesn't just work for things that look like 0 over 0, it also works for things that look like infinity over infinity. But it has to be a fraction and it has to be an indeterminate form. So real quick, maybe a review on indeterminate forms. Indeterminate forms, these are expressions like 0 over 0 or infinity over infinity that don't have a fixed value, right? Like 0 over 0 could actually come out to any real number. It depends on the details of the limit that led to something like 0 over 0. And the same is true for infinity over infinity. Other indeterminate forms include zero times infinity, infinity minus infinity, 1 to the infinity. Let's see, am I missing any? I'm sure I am. We've got indeterminate products, indeterminate differences, indeterminate ratios, indeterminate powers. I think there is another sort of indeterminate power. So let me sneak in here to L'Hopital's rule. Where is that? I think it's, yeah, here we go. Indeterminate forms and L'Hopital's rule. So they should have a list in here. We'll come back and do some of these examples in just a little bit. Proof of L'Hopital's rule isn't exciting. Come on, you son of a bitch. Indeterminate differences, indeterminate form, powers. Yeah, okay, so 0 to the 0 is also an indeterminate form, as is infinity to the 0. So 1 to infinity, 0 to the 0, of course, and infinity to the 0. Basically, when you have two things that are fighting each other, right, like 0 times infinity, those are fighting each other. The infinity wants to get big, the 0 wants to make it small, or infinity minus infinity. Of course, this guy wants to get big, and this guy wants to make him small. 1 to the infinity, 1 wants to stay 1, but if you raise it to the infinity, maybe something funny could happen. 0 to the 0, well, you know that if the base of a number is 0, then it should be 0. If the exponent of a number is 0, it should be 1. So these guys are definitely in combat with each other. And similarly here, anything raised to the 0 should be 1, but infinity raised to any power should be big. So these are all fighting each other. So this is your exhaustive list of indeterminate forms. But the only ones to which you can apply L'Hopital's rule are 0 over 0 and infinity over infinity. So what does it look like to use these things? Well, I can use L'Hopital's rule to find the limit as x goes to 0 of sine x over x. You may remember this limit. This was one of the special trig limits we needed when we were figuring out the derivative of sine. And our argument to show that this limit comes out to what it does was fairly complicated. It involves drawing a figure, a geometric argument, involved a circle and 2 triangles, and then a squeeze theorem argument. But now we can do this very quickly. Look, if I plug in 0, this looks like sine 0 over 0, and the sine of 0 is 0. So this looks like 0 over 0. And I put it in those quote bunnies because 0 over 0 isn't necessarily a number, it's an indeterminate form. So I'm saying I'm not responsible for this. Since this looks like 0 over 0, the theorem tells me I can use L'Hopital's rule. And the way I like to indicate that I'm using a L'Hopital's rule is a little L-H above my equals sign. So the limit above is equal to limit x to 0. I take the derivative of the top and the derivative of the bottom. And this equality is due to L'Hopital's rule. So it's nice to let your reader know where it's coming from. Now I try again. So if I plug in 0, here I get cosine of 0 over 1. The cosine of 0 is 1. So this is 1 over 1, which is 1. And that's what this limit is. Limit x goes to 0, sine x over x, that's 1. That's our special trig limit. There's lots of other things like this. Maybe I want to try and take the limit as x goes to infinity of x squared over e to the x. Well, here, as x goes to infinity, we know x squared goes to infinity, and e to the x also goes to infinity. So this looks like infinity over infinity, which is another indeterminate ratio. So I can use L'Hopital's rule to rewrite this limit as the limit as x goes to infinity, the derivative of the top, which is 2x, over the derivative of the bottom. The derivative of e to the x is still e to the x. This still looks like infinity over infinity. If you plug in infinity, 2 times infinity is infinity, e to the infinity is infinity. So I need one more application of L'Hopital's rule. So now the derivative of the top is the derivative of 2x, that's just 2. The derivative of the bottom is still e to the x. So this is 2 over e to the x. That's 2 over infinity. No need for quote bunnies there because 2 over infinity is 0. And that's it. So the limit as x goes to infinity of x squared over e to the x is 0. Another way of thinking about this is that e to the x grows so much faster than x squared that when you start dividing these, you put in a big number for x and divide x squared by e to the x, that's going to come out to a very small number because the bottom grows much, much faster than the top. And really that's what L'Hopital's rule is saying. Rather than comparing the size at any one place, you can compare how fast the functions are growing. Remember, derivatives are rates of change. All right, we'll do one more example like this. I could look at the limit as x goes to 1 of the natural log of x divided by x minus 1. If I just plug in 1, I get ln 1 over 1 minus 1 is 0, and ln 1 is 0 also. So this looks like 0 over 0. So rather than trying to futz about with some algebra, and here really there isn't any algebra trick that would save the day, I use L'Hopital's rule. According to L'Hopital's rule, limit is as x goes to 1. According to L'Hopital's rule, I take the derivative of the top, which is 1 over x, divide by the derivative of the bottom, which is 1. And here I'll get 1 over 1 divided by 1, which is just 1. So the limit as x approaches 1 of ln x over x minus 1 is 1. The question now is, how do I handle the other indeterminate forms, like indeterminate products, powers, differences? Right, so the other indeterminate forms were not indeterminate ratios, they weren't fractions. Sometimes you've got like infinity times 0, or infinity minus infinity, or 1 to the infinity, this sort of stuff. In each of these cases, you need to do something a little bit different. So if lim x to c, f of x times g of x looks like 0 times infinity, that is f of x goes to 0 and g of x goes to infinity, then you can rewrite, I'll put this in quote bunnies again, then you can rewrite. So again, remember the idea here is that f of x is going to 0 and g of x is going to infinity. And you can rewrite this limit as lim x to c. I can leave f of x upstairs and shove g of x downstairs as 1 over g of x. It's a sneaky algebra trick. Go ahead and check. F of x divided by 1 over g of x, you would flip this and multiply. It's the same as f times g. But now f is going to 0, so the top is going to 0, and g is going to infinity, so the bottom is going to 1 over infinity. This is now 0 over 0. So you could use L'Hopital's rule. that's how we handle the products. Indeterminate differences, that's going to be a multiply by the conjugate type thing. Or maybe just a put together and have common denominator type thing if you're lucky. Indeterminate powers, these are going to require taking logs and working with a little bit more carefully. So let's look at an example here. I'll grab one from the book. How about, yeah, screw it. Lim x to 0 plus x times ln x. You know that as x goes to 0, x goes to 0, so that first piece looks like 0. And as x goes to 0, the natural log of x goes to negative infinity. So this is definitely an indeterminate product, like 0 times infinity. And I can handle it by shoving the ln x downstairs as 1 over ln x, or I could shove f of x downstairs, the x here, as 1 over x. And I'm going to do the second thing there, just to get a little variation, but either one would work. So I can leave the ln x upstairs and send the 1 over x, or I can send the x downstairs as 1 over x. Same trick. Now as x goes to 0 from the right, the top is going to negative infinity. And as x goes to 0 from the right, 1 over x, the bottom here is going to positive infinity. And this is an infinity over infinity. The negative doesn't matter. So now I can apply L'Hopital's rule. So this, according to L'Hopital's rule, is equal to the limit as x goes to 0 from the right of the derivative of the top, which is 1 over x, the derivative of ln x, over the derivative of the bottom. Well, what is the derivative of 1 over x? That's the derivative of x to the negative 1. That's negative 1 times x to the negative 2, or negative 1 over x squared. We can do some algebra. I get lim x to 0 plus 1 over x times negative x squared over 1, flipping and multiplying. That is lim x to 0 plus, cancel the x's, you just get negative x. And that is 0, because as x goes to 0, as x goes to 0, negative x, of course, goes to 0 as well. Alrighty. So that's the game for indeterminate products. You shove one of the functions downstairs as its reciprocal. That will allow you to rewrite an indeterminate product as an indeterminate ratio. So taking a 0 times infinity to 0 over 0, or infinity over infinity. Let's do one more like this. What do we have here? I'd like to do one more. It's a little challenging. But they only do the single example there. So we're going to need to grab something from here. Let's see, indeterminate products. Oh, I got one. Here we go. I could do, for example, x times e to the negative x. So you know that as x goes to infinity, x goes to infinity. And as x goes to infinity, e to the negative x goes to 0. Remember the graph of e to the negative x looks like this. So as you wander off to the right, he's going to 0. And this is another case where I get out infinity times 0. So another indeterminate product, which means I need to pick one of these guys to send downstairs. And in this case, it's nicer to send the e to the x stuff downstairs. So I get lim x to infinity, x divided by 1 over e to the negative x. And we can clean it up algebraically a little bit before we even get to work on that, because 1 over e to the negative x, that's just e to the x. And now this, top is going to infinity, bottom is going to infinity. So now I can use L'Hopital's rule. The derivative of x is 1. The derivative of e to the x is e to the x. And now when I take my limit, I get 1 over infinity. That is 0. So L'Hopital's rule itself is not hard to use. Sometimes, though, the algebra that leads you, or that you need to do to get to a place where you can do L'Hopital's rule is a little tricky. I'm going to show you how to handle an indeterminate power next. I'm not going to cover indeterminate differences explicitly. I think they're a little bit boring. You guys can sort them out. You just have a common denominator. Maybe you multiply by the conjugate, and that will turn them into an indeterminate product or an indeterminate ratio. But indeterminate powers, those are tricky. And there's kind of two classic examples here. You've got 0 to the 0 and like 1 to the infinity. So if f of x, let's say lim x to c, f of x equals 0, and lim x to c, g of x equals 0, then lim x to c, f of x raised to the g of x is going to look like 0 to the 0. And if the base goes to 1 and the power goes to infinity, then this would look like the limit f of x to the g of x coming out to 1 to the infinity. In both cases, we use logarithms. So there's a reason why we harp so much on logarithms. They're so goddamn useful, right? They were super useful when we learned logarithmic differentiation, allowing us to take weird powers and turn them into multiples. But we're going to do the same thing here. We're going to take weird powers and turn them into multiples. So a logarithm will allow me to turn something like 1 to the infinity into something like infinity times 0. And from there, I can do precisely the sort of stuff we were doing here. But it's going to require a little bit of luck. I'd like to show you through an example, and the easiest example of this is find lim x to 0, 0 plus f of x, where f of x is x to the x. Okay. Well, as x goes to 0, this definitely looks like 0 to the 0. So I'll say lim x to 0 plus f of x would be lim x to 0 plus x to the x. This is 0 to the 0, which is indeterminate. So instead, I'm going to take the natural log. The natural log of my function here is the natural log of x to the x. And using that property of natural logs, that powers can come down and chill out front, this is x times ln x. So now rather than taking the limit of the original function, I take the limit of the log of my function. Lim x to 0 plus x times ln x. Oh, didn't we just do this one? We did, didn't we? This looks like 0 times negative infinity. So I can rearrange. Last time I left the ln x upstairs and shoved the x downstairs. I'll do it the same way this time because that's a little cleaner than doing it the other way. But I could shove the ln x downstairs as 1 over ln x. That's also an option. Now when I plug in 0, I get negative infinity over positive infinity, which means I can use L'Hopital's rule. And I get lim x to 0 plus 1 over x divided by negative 1 over x squared, which is lim x to 0 plus of negative x when you cancel, which is 0. But that doesn't mean that the limit I was after at the start is 0. That means that the natural log of my function goes to 0. So ln of f of x goes to 0 as x goes to 0 plus, which implies f of x itself goes to e to the 0 as x goes to 0 plus. In other words, you can exponentiate through this relationship. E to the ln of f of x is f of x. E to the 0 is e to the 0, and that's 1. So the limit as x goes to 0 plus of f of x, in this case, is 1. The graph of x to the x you've probably never seen. It's a pretty weird looking function. If you want it to be defined, you can only plug in real numbers that are bigger than 0. But if you define it piecewise so that it's defined at 0, the height here is 1. He dips down for a minute and then he explodes way up. So this is f of x equals x to the x with the hole at 0 there, 0, 1 filled in because I know that that limit is 1. Okay, there's one other very important example of an indeterminate power. And that's the limit as x goes to infinity of 1 plus 1 over x to the x. Here, the base, the inside, we know the 1 over x piece there will go to 0. So this is 1 plus 0, all raised to the x. Well, that's going to infinity. And that's an indeterminate power. So the sort of formal way to do this is you say L is the limit as x goes to infinity of 1 plus 1 over x to the x. And you take natural logs. The natural log of L then would be the natural log of this limit, and then I can pop the limit out. So we'll just say it's the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. And then this x, this power, using log rules, can come down again. This would be x times the natural log of 1 plus 1 over x. And this guy, if you go plugging in infinity, looks like infinity times the natural log of 1, which is infinity times 0, which is an indeterminate form. In particular, it's an indeterminate product. So taking the logarithm in an indeterminate power always gives you an indeterminate product, which we then turn into an indeterminate ratio, just like in the previous example. And here I'll move the x downstairs as 1 over x, because it's easier to differentiate 1 over x than it is to differentiate 1 over this thing, although that would work also. And we can observe that the top is still going to ln1, and the bottom is now going to 0. ln1 is 0, so this is 0 over 0. So we can apply L'Hopital's rule. According to L'Hopital's rule, this limit is lim x to infinity, the derivative of ln of 1 plus 1 over x, which is going to be 1 over 1 plus 1 over x, times the derivative of 1 plus 1 over x. The derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. And downstairs, the derivative of 1 over x is negative 1 over x squared. So altogether, I've got lim x to infinity, 1 over 1 plus 1 over x times negative 1 over x squared, and then I flip this guy up, he's negative x squared over 1. We cancel schmancel. And now, when x goes to infinity, this piece is just 1. This piece will go to 1 over 1 plus 0, which is 1. So the natural log of L is equal to 1, which means L itself is equal to e to the 1, or just e. And you may recognize this limit, the limit that we started with. That's the definition of the number e that's used in most pre-calculus and algebra classes. In this class, we used a slightly different definition because it was more convenient as we started taking derivatives. But this is the kind of standard definition of the number e. This procedure of taking natural logs and bringing the power down to turn the indeterminate power into an indeterminate product, and then shoving one of the functions downstairs to turn the indeterminate product into an indeterminate ratio, then applying L'Hopital's rule, then going back and undoing the log to get the answer, is a little bit complicated. But it's the only thing that's really tricky when it comes to working with L'Hopital's rule. And again, it's not the L'Hopital's rule step that's hard. It's the algebra steps that you need to do to justify the use of L'Hopital's rule. So that, I think, is sufficient for L'Hopital's rule itself. The other thing that we want to talk about this week is curve sketching, just a little bit. But unfortunately, that's going to have to wait because I have some other things that I need to get started on right now. So I will end this video here, and we will pick it up from here next time. All right. I wish you guys all the best. If you would like trouble with anything, do not hesitate to ask for help, and take care.